I'd like to welcome Sungho Shin for this fascinating webinar that we'll have today. Sungho is an incoming assistant professor at the Chemical Engineering Department of MIT, and he's currently a postdoc researcher in the Mathematics and Computer Science Division at Argonne National Lab. He received his Ph.D. from the University of Wisconsin-Madison with advisor Victor Zavala. He was also a summer intern at Los Alamos National Laboratory and Argonne National Laboratory. His research interests include model predictive control, optimization algorithms, and their applications to large-scale energy infrastructure, such as natural gas and power networks. He's the main developer of the nonlinear optimization solver, MadNLP.jl, and the automatic differentiation algebraic modeling tool, ExaModels.jl. He was a winner of the W. David Smith Jr. Graduate Publication Award and also a couple other awards as well. We are honoring him today with this webinar, in particular for the W. David Smith Jr. Graduate Publication Award. And so I'll turn it over to him now for this presentation. Welcome.
Thanks, John, for the introduction. And thank you for the invitation to give this webinar today. So I'd be very excited to give this presentation. So today I'll be sharing some of our recent results for the large-scale nonlinear optimization and running them on the GPUs. We're gonna summarize some of our key achievements so far, and then we will also talk about some of the open questions. So we are still doing the baby step, and we are in the phase of, oh, look, this is working, and then there are a lot of more things to do. So I'm going to be also talking about some of the open question and some of the future prospects, what kind of application we can target with these capabilities. And this work is done in collaboration with two of my colleagues. The first is Francois Paco. He has done a lot of amazing job in terms of improving the MadNLP.jl and then applying it to the large-scale optimization problems. And he's now at Mainz, Paris in France. And Mihai Ionescu, he's my postdoc supervisor at Argonne National Laboratory. And through this project, we have developed two open source optimization packages. The first is MadNLP.jl. John briefly introduced about that. And this is the nonlinear optimization solver, and it runs on the CPUs as well as the GPUs. And ExaModels is an algebraic modeling tools like Pyomo, Casadi, and Ample. And it has the capabilities to evaluate the sparse Hessian and Jacobian on the GPUs, which is also quite critical for performance optimization on the GPUs. So let me start the presentation with a brief statement of the key takeaway from this presentation. First of all, accelerated computing is offering quite a lot of significant opportunities for systems engineering. In systems engineering, we have been trying to solve large-scale and complex optimization problems, but many times the capabilities of the single CPU system is quite limited, so we cannot go after extremely large-scale and complex problems. But accelerated computing provides a really nice way to accelerate the solution and make it scale up so that we can target larger scale problems. So the key achievement that we have accomplished so far is the development of the nonlinear optimization solver running on the GPUs. So we have applied this to the large scale AC optimal power flow problems, and we were able to achieve more than 10 times speed up compared to the largest instance of the AC optimal power flow problem. And that's against the state-of-the-art open source solver IPOpt. And this means that we can optimize the overall operation of the whole Eastern interconnections in just less than 20 seconds. And if you solve that problem, the same problem on the CPUs, it takes about 200 seconds. So it is indeed 10 times speed up. And it is not just us, and there are a lot of other researchers who are working on the area of intersection between the accelerated computing and optimization in general. And linear programming is another interesting area. So people have been developing the first order-based method called primordial hybrid gradient method. And this is also quite amenable for parallelization on the GPUs. And people have been developing this tool, and they have comparable performance with Groby. So there are a lot of promising and interesting results that are being reported in the literature. And then indeed, there are a lot of opportunities to use GPU computing within the optimization area. So with this capability, we are envisioning to massively expand the role of optimization in different applications. And these two are some of the examples that I like to talk about these days. So first is the extremely large-scale optimization problems. So let's say that we want to make the coordinated decision for the coupled infrastructures, for example, the transmission system, distribution system, natural gas networks, and you can basically go on, and it is a giant coupled system. And how can we model and optimize that kind of problem efficiently? I believe GPU can provide a very promising solution for this type of extremely large-scale optimization problems. And the second example is the optimization problems that embed AI models. And especially in the industry, we have been doing a lot of these type of tasks, especially in the context of surrogate modeling. So people have been training the surrogate model and embed that into the optimization process. But people have been trying to use mostly the linear type of surrogate models. But we eventually want to expand these capabilities into a nonlinear regime. And then for doing that, the best way to do is training the neural network and embedding that into the optimization process. And if you want to do that, then basically you want to evaluate the sensitivity of the neural networks on the GPUs, because that's the only way to do that in a scalable way. And then you want to embed that into the optimization process. And if you want to facilitate this overall implementation, you really want to develop an optimization solver that runs entirely on the GPUs. So these are the kind of the areas that this optimization on the GPU can make impacts. And then we are quite excited to have some of the promising results. And then I'm going to be sharing these results today. So this is the outline of today's presentation. I'm going to be starting with the motivations on why did we start to develop the optimization capabilities on the GPU. And in the second part, I'm going to be giving you a short tutorial on the nonlinear optimization software. So this part is going to be a little bit technical, but here I'll try to describe what are the specific software capabilities that we are trying to implement on the GPU. And in the third part, I'm going to be talking about our main contributions, including the implementation of the algebraic modeling systems and sparse automatic differentiation capabilities. And in the second part, I'll be moving on to the implementation of the nonlinear optimization solvers. And then we will conclude the talk with some of the open questions and then the future prospects. So we will start the discussion by first talking a little bit about the digital twins. So digital twins is an emerging concept that is kind of the replacement of the conventional notion of the mathematical modeling. So in that regard, it is not too different from the mathematical modeling, but it is now becoming really a buzzword. And then if you look at the kind of the key idea of why it is becoming an important keyword, and it is coming from the enhanced capabilities that this virtual representation can do. So it is similar to the conventional mathematical model in the sense that it is a virtual representation of a certain physical system. So the physical system can be anything like power network, energy infrastructures, human body, and then robotic system, and it can be the things like that. But the virtual representation has some advanced capabilities. And then the first thing is the bidirectional interaction. So if there are certain change in the physical system, and then the virtual representation needs to kind of update the information in the model so that it can update the parameters, or it can update the model structure so that it can continue to bring the close approximation of the physical systems of interest. And another thing, to be honest, more exciting to me is that it can serve for multiple purposes. So it can be used for the simulation, it can be used for the uncertainty quantification, inverse problems like data assimilation, state estimation, and it can also be used for the decision making, for example, solving the control, operation, and design type of problems. And if you want to have this type of flexibility in terms of what type of computational capabilities it can do, you need to have a certain advanced computational capabilities so that it can support for multiple type of computational tasks. So for example, it should have a certain degree of differentiability, meaning that you should be able to evaluate the first and second order derivative of the model in an efficient way by using the automatic differentiation. And another thing is the modularity and composability. If you're building a very complex system digital twin, you cannot just build everything in one place. The right approach here is basically you do some modular construction of the subcomponent of the model. For example, if you are going after the large-scale energy infrastructure, you build a digital twin for the chemical industry, for example, energy storage system and then power system, and then put together everything by composing that into a larger scale model. So that kind of flexibility should be there in order to kind of apply these techniques to the complex systems. And lastly, this is directly related to today's topic, and that's accelerated computing. And when we're talking about digital twins, we want to apply that to the complex system, not just a simple problem with 4 or 5 variables. And if you want to do that, it is essential to have this accelerated computing capabilities so that you can apply the advanced computational tasks to very complex and very large scale systems. And we also want to apply this to the optimization problems, for example, the inference or the decision-making problems that we are facing in the complex system. So the high-level idea of this our project is that we want to provide these advanced computing capabilities and software infrastructure that allow people to apply this type of accelerated computing techniques to the challenging optimization problems that we are facing in the complex systems. So accelerated computing has actually enabled a lot of progress in the field of AI. So AI models like the GPT model have trillions of parameters in their neural networks. So without the use of the GPU computing, it is very difficult to train and utilize these complex and large-scale neural networks. And accelerated computing is not just used for the AI, but it is the general purpose computing framework, and that can be applied to different types of scientific computing tasks. It has been used for the fluid simulation, climate modeling, and bioinformatics, and many other fields in the scientific computing. And this is also quite related to some of the recent advancements in the high-performance computing. And we are entering into the exascale computing era. And this means that we now have a single supercomputing system which has the capability of performing 10 to the 18 floating point operations per second. This is quite an unprecedented power. And if you do the calculation, you can see that this is equivalent to 1 million units of iPhone. So this is a really powerful capabilities, and many of the computing power is coming from the GPU. So in order to continue to enjoy the advance in the hardware, and if you want to benefit from this advance in the hardware, it is very important to develop the tools that can harness the power of the GPUs. So in this presentation, we will try to answer this question. Can we harness these capabilities in the realm of classical nonlinear optimization? And what I mean by classical nonlinear optimization is the problems that we are facing in the energy infrastructure operations, such as the optimal power flow, gas network operations problems, and so on. And we also want to solve real-time decision-making problems like optimal control problems, such as the ones that goes into the model predictive control system. And we also want to solve different type of problems that we are facing in operations research and systems engineering. And these are basically the main target problem that we are considering in this presentation. So how does the GPU work? So very simply speaking, it's a parallel computing hardware device which implement a certain type of parallelism, which is called single instruction multiple data parallelism. So the key idea here is that we have a computing system which is equipped with a large number of processing units. So A100 GPU, which is kind of one of the recent GPUs of NVIDIA, has thousands of parallel processing units, and they basically provides massive parallel processing capabilities. But this comes with one restriction, which is that they need to simultaneously execute a single instruction. And this is a little bit different from the multi-threaded CPUs because multi-threaded CPUs can execute more heterogeneous type of instructions. And another restriction is that we typically have discrete or dedicated GPU, and this means that host system, which is CPU, and then the device is kind of separated, and they're only interfaced with a quite slow PCIe interface. And because of this reason, if you want to execute something really fast on the GPU, you really need to minimize the use of the interface between the CPU and GPU. So for that purpose, for that reason, it is very important to ensure that all of your array data reside exclusively on this device memory, and all the execution is performed by the GPUs. So you need to go all the way to the GPU, and you cannot just introduce the GPU acceleration in an ad hoc manner. But this applies to more than niche GPUs, but now there are some interesting development. So a lot of hardware vendors are now producing the architectures based on the unified memory. And this unified memory, the GPU and CPU can kind of simultaneously access to this memory. So this kind of really reduces the overhead caused by the communication between the CPU and the GPU. So for this development, I think there can be some of the interesting things that we can do by using both the CPU and the GPU. But in order to maximize the performance and the throughput that you can get from the GPU, it is still very important to ensure that all of your computation is run by the GPU, not the CPUs. And because of these number of differences and the restrictions that GPUs have, adapting the CPU code into a GPU code is not merely a matter of software engineering, but it is more of the matter of the redesign of the algorithm, because you need to ensure that all parts of your algorithm can be run efficiently on this parallel computing architecture, and then you need to kind of eliminate all the serial portion of the algorithm. And this was particularly the case for the nonlinear optimization, especially because of the sparse linear algebra, but we're going to get into that later. So in this context, we embarked on this project called Exascale Computing Project, and basically the mission was to build the software infrastructure for the nonlinear optimization. So actually the higher level scope was a little bit broader. So there are people developing the linear algebra tool, PDE, climate modeling, and so on. But our team at Argonne has been focusing on the development of the nonlinear optimization software infrastructure. And our goal was to basically building the whole software infrastructure, which include the nonlinear optimization solver and automatic differentiation and algebraic modeling system that kind of facilitates the implementation of the nonlinear optimization. And we additionally had several goals we wanted to achieve. And then the first is the performance. Of course, if you look at the price tag of the GPU, it doesn't make sense to have some marginal improvement in the performance, but actually we wanted to have at least an order of magnitude speed up compared to the contemporary CPU devices. And secondly, we also wanted to have a portability. So typically when people talk about GPU nowadays, that typically means the NVIDIA GPU, because NVIDIA GPU, their hardware has amazing capabilities, and also they have a lot of support for different type of low-level operations. So NVIDIA seems to be the most widely used GPU hardware so far. But at the same time, as an academician, we want to also support different type of GPU architectures. Also, the existing exascale systems, such as the Frontier and Aurora systems, were built based on the AMD and Intel GPUs. So our end goal is basically running the optimization algorithms in the exascale system. So we aim to develop portable software implementation of the nonlinear optimization tools. But at the same time, it has been a little bit challenging because some of the low-level library we really need to rely on are only available on NVIDIA system. So far, we are not fully supporting AMD and Intel GPU, but we are only partially supporting them. But in the future, we are interested in extending the capabilities so that we can support multiple GPU architectures. And also we want to solve practical problems. So we believe one of the most important problem for the nonlinear optimization space nowadays is the AC optimal power flow problems. And these are the problems that independent system operators for the transmission systems solve to compute the location marginal price of, for the operation. And this is quite an important problem. And it is expected to be even more important in the future because of the decarbonization efforts. So we decided to use this as a benchmark problem, but of course, we are building the general tool, so it can be also applied to different type of problems. And we will also see some of the problems that are not AC optimal power flow problems in the later part. Yeah, and we decided to build these tools based on this Julia language. So I guess nowadays a lot of people are using the Julia language of sometimes for teaching and sometimes for implementing some numerical algorithms. But Julia was really a game changer for us because of a lot of its features. So in this part, I'm going to be mainly talking about its performance, productivity, and portability. First, in terms of the performance, Julia really doesn't have any performance compromise compared to other fast languages. So this is a little bit of the performance benchmark of different programming languages, and it compares C++, Julia, C, Rust, Python, and many other languages. And you can see that if you exclude the just-in-time compilation time, you can see that Julia is one of the fastest languages, and it is as fast as C, C++, Fortran. So as long as you already spent the time for the compilation, there's not really a compromise that comes from the use of the Julia, which is really nice. And still, the Julia syntax, if you look at the Julia syntax, you can see that it is very simple and high level, and it's very easy to use as Python, R, and MATLAB. So oftentimes when you develop the performance critical software, what happens many times is that you need to develop the performance critical part in the fast languages like C or C++, and you still need to develop the user front end, for example, for the Python and MATLAB. But we really didn't have that problem, which is so-called two-language problem, and we were able to develop everything based on the Julia. And there was a big performance boost for us. And this is a little bit of the demonstration of for that. So IPOpt and MadNLP is basically the same implementation of the interior point method. But of course, IPOpt has a little bit more feature, but MadNLP also have a lot of its own thing because of the compatibility layer for the GPUs. And you can compare the lines of the code, and you can see that MadNLP is much more concise. And this is kind of revealing that you can basically develop the software tools much faster by using this Julia language. And another thing that we really liked about Julia was this multiple dispatch feature. And with this feature, you can develop a numerical software with high-level abstraction, but at the same time, you can do an arbitrary level of specialization as you go down to the lower-level functions. So here I have a simple demonstration. So let's say that we want to implement certain nonlinear optimization solver. And let's say that we want to do some matrix multiplication here. We want to multiply B and C in the place of A. And these type of capabilities and this type of function is quite prevalent. And then when we want to do some low-level performance optimization, for example, for this matrix multiplication, and you can actually dynamically dispatch this function to different type of functions depending on the observed type in the runtime. And that's called multiple dispatch. And by using these capabilities, you can keep your high-level code very simple and nice. But at the same time, if you want to specialize for a particular data type, you can do this specialization in these low-level functions. And this is particularly relevant for developing the portable nonlinear optimization solver that can support different type of GPU architectures. So we have been using these capabilities quite extensively, and this has been helping us to develop the solver in a concise way, but still we don't lose any performance. Okay, so this was a high-level description about our project, and now I'll be moving on to the next part, which is going to be the short tutorial on nonlinear optimization software. So nonlinear optimization algorithm starts with the definition of the problem. So we basically have decision variable X, objective F, and then the constraint C. And in classical systems engineering applications, we are dealing with the problems with very large scale variables and constraints, but the problem is still very sparse, and we also have the smoothness. And the reason for the smoothness is basically a lot of the objective and the constraints are deriving from the physics, which is expressed in terms of the analytical functions. And that means that we have the capabilities to evaluate first and second order derivative of the functions in a very efficient way. And that can be utilized within the optimization algorithm. And many of the existing tools are built based on this availability of the sensitivity information. And also we have large number of variables and constraints. So it can go up to millions of variables and constraints for the large scale cases. And this is kind of obvious if you think about like optimizing the power grid and things like that. But still, the problem is highly sparse, meaning that each of the constraint or each of the objective function term is only dependent on a small number of variables. And thanks to this, if you look at the Hessian and Jacobian, it becomes a very sparse matrix, and you only have a small number of non-zeros in the matrix. So as long as you can exploit this sparsity, even if the size of the problem is very large, you can solve the problems pretty efficiently. And that kind of features are already built in the state-of-the-art optimization tools like IPOpt. And interior point method is the state-of-the-art algorithm for solving these type of problems. So there are, of course, some of the alternatives like sequential quadratic programming, augmented Lagrangian method, and so on. But interior point method is the most widely used method nowadays. So the key idea of the algorithm is that we replace the inequalities with certain smooth log barrier function. And what's nice about this is it eliminates the combinatorial aspect of the problem. And now you can treat everything based on the smooth nonlinear equation. So as long as you can write down the first order condition, and then you can just repeatedly apply the Newton step to find the solution of that nonlinear equation. And this linear system is called KKT system. And by solving this problem, we can basically obtain an effective search direction. And then you can apply a certain type of criteria to determine the step size and apply it to find the next step, prime major iterate, and you can repeat this procedure over and over until you find the solution. And this is basically the very high level idea of nonlinear optimization algorithm. And one thing I like to mention before we move further is that this KKT system is not typical for type of linear system, and this is because it is suffering from very extreme degree of ill conditioning. And this is because we are eliminating the inequality constraints and we are introducing the log barrier function instead. So as you approach to the solution, some of the inequality constraints becomes activated, and that leads to quite significant perturbation in this sigma term in the KKT system. So typically, we are dealing with an extremely ill-conditioned problem, and oftentimes it causes some of the numerical issue. So we need to employ a very robust and efficient direct linear solver in order to find the step direction by solving this KKT system. So now I'll be moving on to the software part. So here I'm going to be describing what are the key software packages that implements the specific type of the specific part of the computation within the nonlinear optimization algorithm. So the first is the algebraic modeling system, such as MPL solver library, JUMP, and XADI. And these algebraic modeling systems applies basically first of all it provides the user front end where the user can specify the objective and the constraint functions by using the algebraic expressions. And then when nonlinear optimization take over and apply the algorithm to solve the problem, it also provides the capabilities to evaluate the sensitivity information that goes into the KKT system. So nonlinear optimization problems, when it's necessary, it queries this information to formulate this KKT system. And then nonlinear optimization solver also employs certain sparse linear solver to find the solution of this KKT system. And fortunately, on the CPU, there are some of the existing very effective tools that are available. And these tools include MA27 and Paradiso for the extremely large-scale problems. And then once the step direction is computed, it can proceed with the nonlinear optimization algorithm. So nonlinear optimization solver like IPOpt and Nitro orchestrates the overall procedure, and it basically applies the iterations of the interior point method. So these are the basically three main software packages that allows to apply the numerical nonlinear optimization algorithms. But one thing to note here is that many of these tools like AMPL, IPOP, MA27, they have been developed in very, very back in the days. So some of these tools are developed even before when I was born. So they are mostly optimized for the CPU and they are not built for the GPUs. So if you want to implement these capabilities on the GPU, we will need to implement something completely new. Mostly the same idea, but we will need to develop the tools that are optimized for the GPU, and we want to develop the tools for example, algebraic modeling system, nonlinear optimization solvers, and the sparse linear solvers. So fortunately, there are some of the available sparse linear solvers, but they cannot be directly utilized within the nonlinear optimization algorithm. So we're going to be getting to that later. So we're going to be focusing on the development of the algebraic modeling system and then nonlinear optimization solvers. Okay, so now I'll be moving on to our contribution on implementing algebraic modeling systems for the GPUs. So the most challenging part is the automatic differentiation. So this is because in the end, algebraic modeling system typically needs to provide the capabilities to evaluate the sparse Jacobian and Hessian. That seems to, that there is oftentimes the computational bottleneck in many of the implementation. So we typically apply automatic differentiation method to evaluate the derivative information. And automatic differentiation is an alternative method for the finite differencing, symbolic differentiation, and handwritten derivative code. And it is well known that it is superior in terms of efficiency and accuracy and also for the convenience. So automatic differentiation directly converts the function derivative code into a derivative evaluation code by using the certain algorithmic strategy. And automatic differentiation has been the state-of-the-art technique for the derivative evaluation for many of the numerical optimization software. So it has been implemented in MPL solver library and JUMP, XADI, and so on. And PyTorch, the machine learning frameworks like PyTorch and JAX have some automatic differentiation capabilities, but they are typically optimized for the vectorized operation for the large-scale dense type of problems. So in principle, we can use that to evaluate the sparse Jacobian Hessian, but they are not optimized for the use for the sparse problems. So that's why we have kind of tried to develop our own sparse automatic differentiation tool that runs on the GPU. But actually, if you think about how do we evaluate the sparse automatic differentiation for the general type of sparse function, and how do we parallelize that, there's actually quite a challenging computer science question. And our goal is developing the software for the nonlinear optimization, but we are not trying to advance the field of the automatic differentiation. So this is quite challenging problem. So, but rather than developing the tool that can be applied to any type of computer programs, we decided to develop certain domain-specific library that can target a large class of large-scale optimization problems that we are facing in the practical application. And that is built based on this idea called SIMD abstraction. And this focuses on this observation for many of the large-scale optimization problems. So these problems typically almost always have a certain repeated pattern. And one of the great examples is the AC optimal power flow problems. So even if we are applying this type of modeling paradigm for extremely large scale, for example, the entire US power grid, still those problems can be very concisely written in the mathematical term. And this is because there are some of the very repeated patterns, and this pattern just repeats over and over, and only changing part in the problem formulation is the data that goes into this same pattern. So if you basically kind of generalize this observation and derive a certain optimization abstraction that kind of captures this repeated pattern, you can basically formulate the problem in this way. And we call this formulation SIMD abstraction. In SIMD abstraction, what we do is we basically express the objective and the constraint functions into by the summation of the single instruction repeated over multiple data. And for the flexibility, we allow these different type of parent to be just a handful number of parents. And we basically apply the same strategy for the constraints. And in this way, we can specify a large class of nonlinear optimization problems by using this structured format. And when we are designing the user API for the ExaModels.jl, we kind of require the user to specify the model equations by using the iterators. And if you specify the constraints and objective function in terms of the iterators, the key benefit is that you basically can separate what are the instructions that is repeated and what is the data over which this instruction is repeated. And then once we have this data, we can store this data in the structured format, and this really facilitates the implementation of the parallel automatic differentiation. And once we have this structured data, only thing we need to do is we apply the standard reverse mode automatic differentiation for each of these computational patterns. And then from there, we can basically obtain a compiled AD kernel. And then that AD kernel is executed over this multiple data. And this provides a very straightforward way of implementing sparse automatic differentiation on the GPUs. So this is a little bit of the performance benchmark where we compare the AD performance for different algebraic modeling platforms. So here we are comparing the speed of sparse Hessian computation, which happens to be the bottleneck in many cases. And we have compared JUMP, which is the Julia-based automatic differentiation system, AmpleSolver library, which is the classical one, and ExaModels running on CPUs, multi-threaded server CPUs, and AMD GPU, and NVIDIA GPU, and Intel GPU as well. So here, the point is not like which GPU is better than the other, because they have a very different type of price range and then the intended use. But the point is that we can run on different type of GPU architectures, and we were able to compare the performance of between one another. And the key observation here is that for the large-scale instances, so these instances have included AC optimal power flow and some of the standard benchmark problem, quadrature NPC problem, and distillation column optimal control problem. And for the large-scale instances, ExaModels.jl running on NVIDIA GPU was the fastest option. Can you hear me well? Okay.
Yeah, we can hear you.
Yeah. So the main observation here is that ExaModels.jl running on the NVIDIA GPU was the fastest in many of the large-scale cases. And if you compare the performance against the jump running on the single-threaded CPUs, you can almost achieve more than 100 times speed up. And ExaModels.jl running even on the single-threaded CPU were quite significantly faster. And this also reveals that this type of SIMD abstraction-based automatic differentiation also facilitates the efficient evaluation of the derivatives even on the CPUs. And we could also support all major classes of GPU architectures, so that was also a plus. So yeah, this result indicates that sparse AD with the SIMD abstraction is basically a game changer for the nonlinear optimization automatic differentiation, and this really enables the efficient derivative computations on the GPU. So with this tool, now the automatic differentiation time in the GPU becomes really a tiny portion. So everything else, most of the time is spent for the sparse linear algebra and the internal computation within the nonlinear optimization solver. Okay, now I'll be moving on to the next part, which is the nonlinear optimization solver on the GPUs. So the main challenge that we have faced when we first tried to think about how do we kind of resolve the issue for the nonlinear optimization is that sparse linear algebra is much more difficult, and we need to completely redesign the sparse linear algebra method for the GPUs. And the main challenge is coming from the difficulty of applying the standard LBLT factorization method. So on the CPUs, what we have done so far is basically factorizing the sparse KKT systems into a lower triangular block diagonal and the upper triangular matrix, and then apply the back substitution to basically solve these systems. And it requires a factorization of this matrix, but the factorization for the indefinite matrix is a little bit more challenging compared to the factorization for the positive definite system. And that's because the factorization process itself is numerically unstable. So in order to ensure the numerical stability, you need to somehow dynamically adjust the order of the elimination. And if you don't do that, the factorization typically fails because of the numerical issues. But at the same time, if you think about the ways to parallelize that process, it is very dynamic and sequential process. And because of this, there is not really a good way to parallelize this operation. And this has been basically the major bottleneck in terms of the implementation of the nonlinear optimization algorithms on any type of parallel computing devices. So people have been trying to develop optimization method on the GPU still, and then people have been trying to kind of design completely different method, like first order method. For example, one of the examples is the primordial hybrid gradient method, which I mentioned earlier in this presentation. And another approach is still based on the second order method, but applying the iterative linear algebra to solve the KKT system. But this type of method only applies to a certain specific context because iterative solvers can suffer really from the ill conditioning. So you need to kind of reformulate the problem, for example, based on the augmented Lagrangian formulation, and then apply the iterative method. But still, that seems to be introducing a lot of inefficiencies. And because of the nature of the iterative solver, when you're dealing with a very ill-conditioned problem, it is susceptible for the convergence issue. So we still wanted to develop an optimization solver based on the classical second-order-based interior point method with the direct solver, but we just wanted to avoid the use of the numerical pivoting because for numerical pivoting, there doesn't seem to be a really promising way of avoiding that within the parallelizing that in the GPUs. So the first strategy that we came up with is the lifted KKT system strategy. So in this approach, we aim to transform the indefinite KKT system into an equivalent positive definite system. And once you do that, you can factorize the matrix with the Cholesky factorization. And this is a numerically stable process, so you can factorize them without the numerical pivoting. And another nice thing is that CUDA, NVIDIA has also already implemented the sparse Cholesky solver, and that has a very, very good performance. So we could actually utilize that available solver, and we can also kind of now once we have this strategy, then everything can be basically implemented in a straightforward manner. So the idea that we have developed is as follows. We first lift and relax the equality constraints, and we transform them into a slightly relaxed inequalities. So here we're introducing the select variable s, And in order for this to be an exact reformulation, we need to enforce s equals to 0. But what we are doing here is that we allow this s to vary around 0 by a very small amount. Typically, this is set to be the same as the solver tolerance. So it can be 10 to the minus 8, 10 to the minus 6, and so on. And then this modification introduces a particular structure in the KKT matrix. And you can now observe that this whole lower right block, which is colored in red, are now becoming non-singular. And because of this structure, we can apply the Schur complement trick, and then we can eliminate this overall lower right block and then state the equivalent form of the condensed space KKT system. And now you can guarantee that after the application of the standard inertial correction procedure, which is implemented in most of the nonlinear optimization solver, you can guarantee that this part is positive definite. And we call this condensed KKT system. And it's a little bit confusing term. So even if it is condensed, it is not a fully dense matrix. This is a still sparse matrix with a slightly increased density, but we are still dealing with the sparse matrix, and it is a positive definite matrix. And this means that now we can factorize this matrix on the GPU by using the standard Cholesky factorization method. But one of the limitation, I would say one of the potential issue here is that because we are condensing the KKT system that typically involves the matrix multiplication of A transpose A, and D can be also quite have some aggressive values. And because of this reason, this can significantly increase the condition number of this condensed KKT system. So potentially it can cause some of the issues. But at the same time, if you look into the nonlinear optimization literature, there are some promising articles because they say that this type of ill conditioning is very structured. And then because of this structured nature, once you recover the full solution after solving this problem, the effect of the ill conditioning is relatively mild. So, but still, in practical, what we have observed is that there is some of the numerical instability caused by this ill conditioning. But compared to the very severe degree of ill conditioning that we are facing, relatively the numerical performance is stable, but we cannot completely ignore the effect of the ill conditioning here. So this was the lifted KKT system approach. And there's actually another way of doing that, and this is quite a classical approach. But recently, people have been developing the hybrid the KKT system solver based on this classical strategy. And this is called hybrid KKT system method. And the idea is quite similar. So first of all, we are eliminating the inequality block, but we still have the equality block because we haven't relaxed and lifted and relaxed the equality constraint. And as a result of the condensation, we obtain this slightly condensed KKT system. And now what we do is we regularize the equality block instead of eliminating. So here what we do is we add this GK transpose GK block into the first 1-1 block of the condensed KKT system. And by manipulating the right-hand side, we can actually ensure that this is an equivalent formulation. And by choosing sufficiently large gamma, you can actually ensure that this is positive definite. So this means that we can utilize the Cholesky factorization of the 1-1 block. And then now you can solve the Schur complement of this 2x2 block system, and that can be done by solving this particular system. But if you want to directly solve this, you need to explicitly form this matrix, which is fully dense matrix. So we don't want to do that. So instead of that, what we do is that we apply a certain iterative method. So, but I mentioned that like this is extremely ill-conditioned method, so we cannot apply the iterative method. But in this case, you can actually show that by increasing the gamma to sufficiently large value, all the eigenvalue kind of converges to 1 by using this strategy. And then this means that you also have the positive definiteness, so you can just apply the conjugate gradient method to solve this system. So this also provides a straightforward way of implementing the linear algebra scheme on the GPU. So I see one chat here.
Oh yeah, it's just getting everybody ready for Q&A. We have about 5 minutes left for the presentation, then we'll jump into Q&A.
Okay, sounds good. So yeah, and also this has some of the ill conditioning issue potentially, but at the same time, this is happening at the structured manner. So the impact of the ill conditioning is relatively mild, just like the lifted KKT system case. So now we have all the pieces. So we have the algebraic modeling systems that runs on the GPU, nonlinear optimization solver based on the lifted and hybrid KKT system strategy. And we also have the sparse linear solver, which is implemented by NVIDIA. And by using these tools, now we can solve the problems entirely on the GPU, and all the array data stays in the GPU, and then we can perform all the operations, at least majority of the operations on the GPUs. So this is I guess the main numerical result that I'm going to present today. And this is the application of all these three software packages to solve the AC optimal power flow problems. So here we compared against CPU, and CPU is also ExaModels MadNLP running on the CPU and MA27 solver, which is the state of the art. So if you compare the performance with IPO, there can be one or two number of iterations difference. So the number of solution time, the solution time here is pretty much comparable to what you would expect from IPO. Elliptic KKT system and hybrid KKT systems, they're all implemented based on our framework. So you can see the numbers, and actually, as you can observe that as you go into the larger scale optimization instances, actually the speed up that you can obtain from the GPU becomes larger. And if you go to the largest case that is considered here, this is the famous 70 case AC optimal power flow, which covers the entire Eastern interconnect. And for this particular instance, you can see that we can achieve about 10 times speed up by using the GPUs. And in terms of the lifted versus hybrid KKT system, there doesn't seem to be a clear winner. But both of the cases, we failed for one case here, and you can see that you can see some of the impact of the ill conditioning that is caused by the condensed KKT system. So we are losing some of the numerical stability, but this is something that we'll try to address in the future implementations. And here we were able to converge up to 10 to the minus 6. So 10 to the minus 8 is a little bit more challenging. Also, if that is related to some of the limitation of the condensed space interior point method. So this ill conditioning issue is something we'll try to address in the future, but at the same time, it might be the case that this is something that we need to live with if you want to solve the optimization problems on the GPU, because condensed KKT system is much more ill-conditioned in nature compared to the indefinite KKT system that we can solve on the CPUs. And on the right-hand side, we are comparing the performance of different GPU hardware, and we have the result that you are seeing here is based on the 800 GPU, which is kind of the higher end of the GPU that NVIDIA produces. And A30 is like slightly lower grade GPU, and A1000 is the laptop GPU that you can get it on your laptop. So you can see that because 8000 GPU has tiny VRAM, so you cannot solve the largest scale problem. But at the same time, even with the lower end GPU, you can solve the problems, pretty large scale problems, and you can get a significant speed up compared to the CPU based solution methods. And here we apply this to a different type of problem, which is the distillation optimal control problem. And here we wanted to see the effect of the solution, effect of the size of the problem on the solution time. So we have varied the number of time steps in the problem, and then we solve the problem by using the CPUs and the configuration of the GPUs with the lifted KKT system and hybrid KKT system. But before we compare the solution time, I would like to first highlight that for the GPUs, quite significant time is spent in the initialization of the problem. And this is because we want to compute the symbolic factorization of the sparse matrix. And right now, we don't have the implementation on the GPU. So everything is sent to the CPU, and the symbolic factorization is computed there. But typically, for the control application, we can eliminate this time, because in control application, what we do is we resolve the optimization problem with the same structure with only updated data information. So this part of the computation can be regarded as offline computation. And if you want to only compare the online computation, we can only compare the time that is reported in the right-hand side. So here we're going to only compare this online computation time. And if you compare this online computation time, you can also see that lifted KKT system and hybrid KKT system running on the GPU can lead to quite a significant speed up. And then in particular, we can achieve more than 20 times speed up compared to the CPU. So this again kind of reveals that ExaModels and MadNLP and cuDSS running on the GPU provides a really powerful method that can significantly accelerate the computation within the nonlinear optimization procedure. So I have another method today as reduced Hessian approach, but for the interest of time, I'm going to be skipping this. But if you're interested in this idea, feel free to contact me. So some of the remaining challenges are, as I mentioned before, first dealing with the yield conditioning method, which is actually the second point. And then the first point is that we have implemented the lifted and the hybrid KKT system approaches, but these are not the only ways to implement the pivoting free interior point method. There can be alternative strategies like based on the penalty method and augmented Lagrangian method. So in the future, it would be interesting to see what are the kind of the best optimization algorithm for especially optimized for the GPUs. And yield conditioning method is something that I talked about before. And in terms of the portability, ExaModels has excellent degree of portability. It can run on the single-threaded CPU, multi-threaded CPU, and all different GPU architectures. MadNLP, we know that we can do the same, but we didn't try to implement everything yet because even if we have that, the Cholesky factorization is not available for the AMD and Intel GPUs. So far, we have been relying on the proprietary Cholesky solver. So in order to ensure that we can run actually on the exascale system, in the future, we are interested in developing certain open source portable Cholesky solver that can run on the exascale systems, in particular on the AMD and Intel GPUs. And another promising direction is exploiting multiple GPU systems. So actually, we have already written a paper about this, but we were targeting a particular class of the optimization problem which exhibits a certain particular structure, which was the two-stage stochastic optimization. But we want to make these tools available so that it can be applied to different type of large-scale nonlinear optimization problems. So in the future, we are interested in developing a distributed version of the GPU architecture so that we can kind of run that on the exascale system and potentially benefit from the multiple GPU systems. So yeah, today I had talked about this accelerated computing for nonlinear optimization and how do we utilize the accelerated computing capabilities within the nonlinear optimization. And I guess the overall goal is that we want to apply this to the practical real-world challenging optimization problems that we are facing in the systems engineering. So nowadays, we want to solve very complex optimization problems for the complex physical systems, such as the power grid operation and energy storage system. And we want to go all the way down to the multi-scale behavior of the batteries. And we also want to kind of flexibly manage the load that comes from the industry and then the residential sectors. And these type of complex optimization problems can be very effectively targeted by using the accelerated computing software. So it can also deal with the complex digital twins based on the physics, and it can also be used for training the surrogate modeling and then solving the optimization problems that kind of embed the digital twins and the surrogate models. So overall, I believe the results that we have reported today is quite promising, and I believe there are a lot of opportunities to solve more complex and challenging optimization problems by using these capabilities. So with this, I'd like to conclude the talk today. So I'd like to thank the funding sources, US Department of Energy and Exascale Computing Project. And these two people have significantly contributed to this project, especially Francois Paco in Mines Paris, and Mihail Aintescu, who's my postdoc supervisor. Yeah, so this is all I have today, and I'll be happy to take any questions.
Fantastic. Excellent presentation. Let's jump right into the questions. First of all, can this developed NLP solver be used with JUMP?
Yeah, so JUMP is gonna, so we have some basic support for JUMP, but the current issue is that JUMP is not necessarily based on the SIMD abstraction. And for nonlinear optimization, it is also very important to evaluate the derivative information also on the GPUs. But yeah, I'll just go into that part. Yeah, so ExaModels.jl, because it kind of stores the data in this structured format, it is very easy to apply the sparse automatic differentiation on the GPU. But if you do it based on the JUMP, you should first go into all the terms in the optimization problems or the term by term, and then kind of restructure the data in this format. And after that, we can apply the parallel automatic differentiation. So we have that interface now. It is an experimental feature, so it can be very, very buggy, but basically it is possible, but it comes with a lot of performance overhead. And that's because we need to go through all the expressions one by one. So the ideal way is expressing the model based on this type of SIMD abstraction. And actually, some of the API are already there. For example, for the gravity system, they have something called constraint template, and jump and Kasadi. And most of the case, if you express them in the vectorized form, then you have the capability to store the data in this structured format. So something that I hope to kind of influence by using this work is that this existing algebraic modeling system, because they already have the capabilities, the only thing they need to do is store the data in this structured format. And as long as they can do that, now like implementing the parallel automatic differentiation can be quite straightforward. And ExaModels can be serving as a backend for them. And then they basically, you can just write some translation layer that converts the expression tree into ExaModels expression tree, and everything can be done in a very efficient way. And if you do that, you don't need to like spend too much time on that translation, because that can be only applied to just the number of parents, not for the whole expression. So that can be done pretty efficiently. But so in the long term, I think it's gonna be possible. But with the existing system, there's some much more work needs to be done.
Okay, fantastic. A related question, another question on that same thread. Can we use this solver? What about mixed integer problems? There's two approaches for that. One, branch and bound, where you could just have the NLP solver because it's faster. It could solve these subproblems, or also outer approximation methods, like where you use an MIP solver to bound or some of the NLP search areas. So what can you say about that? Linearizing to get MILP solvers, and then any integration with others, in particular for mixed integer problems.
Yeah, that's actually something that I also want to ask to the mixed integer folks, but let me just try to explain what I have been thinking about, but this may not be the correct answer, of course. So if there's some, so this is a little bit different because we were targeting extremely large scale single optimization problem. But if you want to parallelize over the branch and bound tree, then it might be potentially beneficial if you can actually solve a bunch of linear optimization problem, for example, certain linear relaxation problem in parallel, and that can be potentially beneficial. And that kind of approach is like in the GPU computing term, it is basically solving a batched optimization problem, basically a bunch of problem, and we say that we solve it in batch. So that means that the approach is going to be a little bit different. And there are some of the existing attempts. So for example, one of our colleagues, so that was not for the linear programming, but it was still for the nonlinear optimization. But he has developed what kind of batched nonlinear optimization solver based on the quite primitive algorithm called Tron. So I think it's possible to implement either like interior point is probably gonna be easier, but you can I think it's simplex method is also possible, but it can be a little bit more challenging. But there are some possibility to kind of apply the GPU computing in that regard. But
Sungho, let me just interrupt really quick. I've got to go start a class at BYU. Junho Park is going to take over for the Q&A. This is fascinating, excellent presentation. Go ahead and continue on. Junho is a co-host. Junho, if you could just stop the recording once it's done. But fantastic presentation. Thank you so much.
Thank you so much for the invitation. Okay, yeah, I just continue.
Do you have it from here? Junho, can you hear me?
Yeah.
Okay, fantastic. Okay, thanks.
Yeah, I just continued answering that question. So linear programming, like how do we solve a large number of linear programming in batch by using the GPU? I think that can be a quite interesting research direction. But based on our research, I don't have much thing to say about how can we do that.
Thank you. For the next question, why hybrid KKT systems seem to require less number of iterations than lifted KKT?
That's a very good question. So hybrid KKT system, if you look at the algorithm, it's actually solving the same indefinite KKT system. So we are not changing anything in the nonlinear optimization problem, and we're actually and as long and if this problem can solve the indefinite system up to the infinite precision, that means that we can actually perform the equivalent number of iteration, equivalent type of iteration for, and it's going to be the same as the CPUs. But because we have like finite precision, that can be slightly changing. But basically, the idea is that it can be in principle, it can be equivalent to the approach in the CPU. But for the lifted KKT system, we are actually changing the problem because we are introducing the slack variable, and we are actually making that as an inequality. And because of that, the number of iteration step can be quite different from the CPU, and that's what we have been observing here. So hybrid KKT system seems to be quite close to the CPU implementation in terms of the number of iterations. But as an exchange, what it needs to go through is that it needs to apply the iterative linear solver to solve this short complement system. That means that each of the iteration can be more expensive because typically you want to apply multiple linear solve because you're utilizing the factorization of the positive definite system here. So each of the iteration, because of this iterative nature of the algorithm, it can be a little bit more expensive. So typically what we have observed is that in terms of the number of iteration, hybrid KKT system is faster, but per iteration basis, lifted KKT system is faster.
Does it actually helpful for managing the yield conditioning, comparing hybrid KKT and lifted KKT?
So far, like, yeah, this is something that we're actively investigating because we finished the hybrid KKT system implementation just a few weeks ago. So we are still looking into like different characteristics of the algorithm. And then what we have observed so far is that they both suffer from the yield conditioning. And that's because if you look at this hybrid KKT system, this is quite interesting observation. And if you increase gamma, actually you can make your iterative solver converge faster, because as you increase gamma, the eigenvalue of this system converges to 1. And that means like if you have sufficiently large gamma, it can even converge in one iteration step. That's nice, but if you increase gamma too large, then that introduces the yield conditioning in this 1-1 block. So if you have too much of the yield conditioning, the Cholesky factorization may just fail, and then you may not compute this solution in up to higher accuracy. So far, like it's also kind of one of the limitation because someone needs to tune this gamma value for this algorithm. So, but still, what we have observed is that if you set this value to 10 to the minus 7, 10 to the minus 8, it works quite reliably. But that means that it is introducing quite severe yield conditioning because of that large value of gamma. So in terms of the yield conditioning, like we don't know yet which one is like handling the yield conditioning better. But yeah, that's something that we are actively investigating.
Thank you. Let's move on to the next question. How do the sparsity and the problem scale in general nonlinear optimization affect the acceleration of GPU rather than special cases like ACOPF?
Yeah, so there can be some of the edge cases because we have been primarily benchmarking our software based on the ACOPF problems. But of course, there are some particular case where this type of method can really suffer. And one case is kind of like it can be rebuilt from the let's see. Yeah, so from here, let's say that we have a fully dense row. In that case, that will make this 1-1 block completely a dense matrix. So this is kind of the reason that condensation strategies, people have been investigating that, but people have been trying to avoid the use of the condensation because of that edge case. And in the worst case, you need to deal with this fully dense matrix. So for the ACOPF instance, we were lucky because the problem is relatively well balanced, because if you look at the transmission system structure, there's no like super node that is connected to everything. Like if that happens, then that can introduce quite severe density, and then that can be kind of the reason that this method cannot be applied. But that was not the case for the ACOPF, and that is also not the case for the optimal control instance where we have this sparsity induced by the time. And I'm not sure. Like, yeah, one case might be the case where we have the allocation constraints where all the resources need to be added together, and that should be like upper and lower bounded by something. And if that kind of the constraint exists, this might be really suffering. But so far, we didn't have the full benchmark case where we can cover all different type of nonlinear optimization problem, because the legacy the benchmark instances, they are built for the CPUs. So if you want to build that build that kind of the benchmark system for the GPU, you need to kind of re-implement everything based on the ExaModels.jl, but we didn't have the opportunity to go through that. But we are still trying to cover at least many type of different type of benchmark problems now on. So we have the implementation of the COPS benchmark, which has been serving as the standard benchmark for the large-scale nonlinear optimization algorithms. And we have a lot of AC optimal powerful instances, and we also have several optimal control instances that we're using. But in the future, it will also be interesting to kind of better characterize what are the edge cases that these methods may fail. I'm sure that they will exist.
Okay, so the next question is, can GPU still significantly outperform CPU in linear systems?
Oh, yeah. So that's what we have observed so far. I'm not sure if I have the result here. Yeah, so lin here is the linear system solution time. And then if you compare the performance of MA27 versus QGSS, you can see that you can see the differences, like about 30 times differences there. So yeah, so in terms of the linear algebra, it can also be quite significantly improving. But still, here, like I would like to also highlight that among these 18 seconds, we are using about 6 seconds in terms of the initialization, and that initialization is performed by, in particular, by MADIS, and that's running on the single-threaded CPU. So I'm not sure whether this can eventually be resolved or not, but right now this is quite a bit of bottleneck, and then if you can eliminate that, we can actually achieve quite significant speed up again. So linear algebra, automatic differentiation, and solver internal computation, they are all quite significantly benefiting from GPUs.
Great. Next question, the last question here. Can you comment on whether applying problem level decomposition, for example, further decomposing the overall KKT system into partitions based on the problem structures, for example, assure complement decomposition benefits the condensed IPM using cuDSS?
Oh yeah, that's a great question. So problem level decomposition, so we also have worked quite a bit about that. So if you have, for example, very long multi-period optimal power flow problem, and then you want to decompose in the time, and then apply, for example, ADMM like method, that's also possible, and we have worked on that. But still, some of the things that we observed about the problem level decomposition, like ADMM, is that someone needs to really tune that penalty parameter. And sometimes it works, and sometimes it doesn't work. And as you know, like ADMM like strategies, they only have guarantee for the convergence for the convex problem. And then like when it converges too slowly, then there's not much of the way to kind of accelerate that convergence behavior. So we also have looked into that, but we kind of concluded that we still want to apply the second order based algorithm, which doesn't require much tuning, and once it is implemented correctly, it converges to the solution in a fast and a reliable manner. So yeah, it is possible, but we still prefer to use the second order based method. And this is kind of related to the question that was asking about the mixed integer program, because for that parallelization over the branch and bound tree, it requires the solution of a bunch of different optimization problems with the same structure, but with and we want to solve the problems in batch. And if you do the problem level decomposition, the situation is quite similar. So you want to decompose it into a large number of independent optimization problem and solve them in batch. So there can be some of the use cases of developing use cases of the batched nonlinear optimization solver. Yeah, and that can be potentially relevant to the problem level decomposition. But based on our experience, this type of second order based method is more effective, and it's more flexibly. It can be more flexibly applied to different applications. Yeah, and you also mentioned short complement, and short complement, and that is a little bit different because you're doing the linear algebra level decomposition, and for the short complement, I think there can be quite significant opportunities. And the result that I showed today about the multi-GPU case, there was implementing the short complement method. So short complement method, when it is implemented correctly, and as long as it exploits multiple GPU, there can be quite significant opportunities there.
Great. So there is no other questions here, so I'm gonna stop recording here, and let's see. I don't have any ability to stop, but yeah, anyway, so thank you so much, Sungho, and for your great presentation and detailed answers for the questions. So, and thank you for joining the session, everyone.
Yeah, thank you all for coming, and thank you for the introduction.
Yeah, thank you.
Thank you. Bye-bye.
Bye.